So there are so many advantage of CFD. CFD is beneficial for obtaining the additional data point beyond experiments, and it helps to conduct simulations wherever physical experiments may not be feasible due to cost, time, or safety constraint. So popular visual output from CFD includes counters like streamlines, which are used for the analysis. So the process is divided into three main stage: pre-processing, solving, and post-processing. So pre-processing is the first stage and most crucial step where the setup of the simulation takes place. So geometry creation. So first of all, we need to basically create a CAD model. If you can get it, import the CAD model into CFD software. Common file format includes step file or IGES file. Ensure the geometry is watertight and close to prevent leakage between the solid and fluid domain, right? And geometry must be continuous to avoid flow irregularities, especially for the aerodynamic shapes like aerofoils or turbine blades. Then we will go for the meshing, but before going for the meshing, we need to define the compressional domain. And compressional domain based on problem type, whether it is of external flow or internal flow. So we need to choose various topologies, rectangular, circular domain, depend on the flow scenario. And for external flow, we need to create the domain external to the object. Like if we take the example here, so this is the aerofoil shape we are having, and whatever the flow we need to understand or behavior we need to understand over the aerofoil, we need to create the domain. So that in this case, this is the case of external flow. So while doing the analysis, in which area the aero within which area we need to see the effect of or the behavior of the flow over the foil, that if we want to understand, so we need to create the domain, and within that domain there should be aerofoil shape. Okay, so internal flow, for the internal flow there is no need for defining this type of domain in the external domain, like we define in the external flow. Internal domain means the domain, the internal area itself, we say it is domain. So we simply by discretizing or giving the meshing to the internal flow, we can go for the next stage. So meshing, after creating the model, after defining it accurately, we can go for the meshing. So generate the mesh for computational domain. To discretize the space, you can see it. So this is the external flow we are having. So we are not giving the we are not going for the discretization of the internal flow. We are not going for the discretization or meshing of the aerofoil. But whatever the external domain we have, we are going for the discretization or meshing of the external flow, right? So mesh density should be aligned with the expected flow features, particularly in the region with the high gradient. So like generally near the wall or boundary layers, pay attention to the boundary conditions, whether it is periodic boundary conditions, ensuring a conformal meshing if possible. So continuity of properties, when a variable velocity, pressure or temperature exists one side of the domain and it re-enters at the opposite side within the same value, that time we can say it is periodical boundary conditions. Like what are the inlet condition we are having? Suppose I am saying, like suppose if I am having the flow, like this is the flow I am having, an x, y, z property at the inlet and should be same at the outlet. Whatever the functions it is having, property and at the inlet and outlet will be same. So that condition you can say it is periodical boundary conditions. Channel flow, if we are taking the example, so simulating the flow in a long channel without modeling the entire length, lattice-like structure, analyzing the repeating units of porous medium or heat exchanger, turbulence simulation, capturing the small scale periodicity in turbulence studies. So these are some points we need to remember about the periodical boundary conditions. Or if we go for the conformal mesh, if you go for the conformal mesh, you can see in the figure. So in this case, the element node, they are interconnected at each and every point. But in this case, there is no interconnectivity between the various nodes, right? So such type of thing we are saying is non-conformal mesh. And here we are saying it is conformal mesh. Again, if we say this is the particular shape we are having, okay, the number of the nodes on this line, maybe suppose 100. So on this line also it will be, it should be 100. If 50 on this curve, then 50 should be on this line also. So this is, we are saying it is conformal meshing. Okay. So next, in material property, we need to define boundary conditions. We need to define for the particular case. So then once we define all the things, we can go for the solver. So in the solver, depend on the type of the condition, whether it is incompressible or incompressible or compressible. So if it is compressible flow, requires mass, momentum, energy equations, while incompressible flow typically involves mass and momentum equations. So decide if the solver will be with of dimensional or non-dimensional parameter. Variable and equations for compressible flow, additional variable like temperature and density are considered. An equation of state can be used to choose the system of the equations. And then we can go for the physical model. Whether we need to go for the turbulence model based on the flow characteristics. So Reynolds average or Navier-Stokes model, whether we can go for it, K epsilon, K omega, SST, or LES large eddy simulation model for capturing the large scale turbulence structures, or DNS direct numerical simulation for resolving all scales of turbulence requiring very fine meshes. So select the additional model if needed, like combustion, eddy dissipation model, or radiation model. So every, depending on the type of the physical model, we have to select the particular model, right? Then solver initialization and setting up. Once you have this type of initialization, proper initialization, then only it is very easy for us to solve, to get the more convergence very quickly. So proper initialization of inlet, outlet, or hybrid initializations influences the conversion speed. Control solution monitoring with the parameter like residuals for velocity and pressure energies. Then set the conversion criteria. So residual falling below 10 to the power 5 minus 5 u to determine whether simulation is to determine when the simulation is complete. Suppose I am having row value. In this case, converging criteria is, if I am saving, so is that converging criteria means what it is exactly. Suppose I am saying 10 to the power minus 5u, then it means the residual value of the previous value iteration and the current iteration, that difference is, if it is goes beyond 10 to the minus 5, then we can say solution is converged and simulation is completed. So post processing, after solving the CFD equation, post processing involves visualizing the results, streamline pressure contours. The results are analyzed to draw conclusion about the flow behavior and validate against the experimental data if available. So important thing is geometry quality. It should be clean, watertight. Geometry is a requirement or criteria for accurate simulations. Meshing strategy, ensuring the mesh refinement in critical areas wherever we need to go for the analysis. Okay, especially boundary layers or region with the high flow gradient. Solving solver selections, understanding the nature of the flow, whether it is steady, unsteady, compressible, incompressible. You need to choose the right solver setting or models. And finally, after initialization, we can significantly reduce the computation time and improve the convergence. Take the example of compressible flow variable. Then in that case, there are so many variables like density, we are having velocity in x, y, z direction, then pressure we are having, and temperature. These are the 6 variables we are having. And in the 6 variables, to solve those 6 variables, we should have 6 equations, right? But by considering this mass, momentum, energy, what we have one mass conservation equation, 3 momentum equation, x, y, z direction, and 1 energy equation. So we have 6 variable, but we have only 3 plus 1 plus 1. So total 5 equations we are having, and we have total 6 variables. So fortunately, in the thermodynamics, we have one more equation that for the ideal case, which is E equals to rho RT. So this can be used as a 6th equation to solve the all to find out the all 6 variables. Okay. So our system should understand that according to the type of the equation or type of the flow, whether it is compressible, incompressible, accordingly it will be selected. Now, if it is of 3D model, then obviously the momentum equation will come. If it is having 2D model, then only two momentum equation, either in the xy or yz or xz. Okay. So from the thermodynamics, we can say pressure, density, temperature are related. As we know, E are related to temperature. If it is not ideal, then we can say we should have the relation between the P, rho and T. If it is ideal, we can directly use P equals to rho RT. So this is the equation of state that allows to connect pressure, density and temperature. So depending on the flow type, select the appropriate model. Depending on the flow characteristics, you need to choose the appropriate turbulence model. For steady state and simulation, popular model includes K epsilon and or K omega or SST K omega. So Reynolds average Navier-Stokes model, K epsilon, shear stress transport model for more accurate simulation of complex flow, especially involving separation. Then large eddy simulation model, LES or DN, direct numerical simulation, might be necessary. So this helps us, this type of models will help us to capture the behavior more accurately. Okay, there are so many other models. If we have the combustion behavior within the system, then we can use the combustion model. There is separate model for that. And if we have the radiation in the system, we can involve the radiation model into the picture as a physical model, and we can apply in the solver. Okay. So defining the solver parameters, as you know, initialization is very important. Proper initialization, accurate initializations will help us to reduce the simulation time or conversion. Generally, for Pan's model, steady state initialization has less impact, but it is critical for LAS and DNS due to flow sensitivity. Okay. So this is all about the unit. This is all about the introduction of the CFD. What we have, the pre-processing, solver and post-processing. So next will be about the various types of methods involved in the CFD. So thank you for this class.